Okay, welcome. So what we're going to be talking about today is how do you calculate the pH when it's during a titration, okay? And so what we've done in the past is we've done calculations using MAVA equals MIVIB, or M1V1 equals M2V2. So let's go back. M1V1 equals M2V2 is simply for dilutions. And so if you have a solution and then you dilute it and you want to figure out what your new concentration is, for example, then you're going to use M1V1. If you have a base and an acid and you're titrating, then what you can do is you can use MAVA equals MIVIB, and basically what it does is at the point where you've reached your equivalence point, typically there's an end point where what happens? What do you see from your eyes at the end point? Typically there's a color change. Awesome. Where there's a color change, usually that's where your equivalence point is. And so what you do is you use this MAVA equals MIVIB equation to be able to figure out either the molarity of the acid or the molarity of the base, depending, or maybe you want to know what volume it takes to reach the equivalence point. And that's what MAVA equals MIVIB basically does for us. But it really doesn't tell us what the pH of the solution is, okay? In order to calculate the pH of the solution, what you basically need is you need your H plus concentration. So depending on what information you're given, as long as you can get your H plus concentration, then what do? What calculation do you use to get pH? Negative log. Awesome. So once you have your H plus, you just negative log it, and that is your pH, okay? So what we're going to talk about here is we're going to try to figure out what the pH is of a solution. Well, if you have a strong acid and a strong base, and they react together in equal amounts, and your concentrations are equal, then you would expect that the pH at the equivalence point would be what? 7. Awesome, okay? Remember, if you have a strong acid with a weak base, then you would expect that your pH would be lower at the equivalence point, and if it's a strong base with a weak acid, you would expect your pH to be higher at the equivalence point. We'll talk a little bit about that and take a look at some graphs. So it says calculate the pH during a titration. The equivalence point of the titration is the point at which exactly enough titrant has been added to react with all the substance that's being titrated with no titrant left over. In other words, at the equivalence point, the number of moles of acid and base, and I want you to circle that a bunch of times, the moles of acid and base are equal to each other, okay? It's really important that you understand that it's moles that are equal, not molarity. If molarity is equal, it has to be that your volumes are equal, okay? So it has to be moles, because the idea is MAVA, for example, moles over liters times your liters. Well, your liters will cancel out, and so when we say MAVA equals MIVIB, we're saying that moles of acid are equal to moles of base in this case, okay? And so it's important to understand, what is this equation telling us? It's telling us that the moles of acid and the moles of base would be equal, all right? So that's MAVA equals MIVIB. So it says, according to stoichiometry. In an acid-base titration, there's a 1-to-1 acid-base stoichiometry. So the equivalence point is the point where the moles of the titrant added equals the moles of the substance initially in the solution. So remember, typically what you have is you have a flask, and so inside of your flask, you put an acid plus maybe some type of indicator, for example, okay? And then what you have is you have a burette, and inside of your burette, you would put your base. And so you start to drop down your base, and as soon as the moles of the base are equal to the moles of your acid, then typically that's where you get that color change. That's your end point. And the way that I look at this is it's almost like you have a preference for Oreos, okay? You love, love, love Oreos. And so the idea would be that acid is going to, and you have your acid inside of here with your indicator, and you drop down the base, and the base is going to react, and it's going to start to react with the acid, because that's what it wants to do, right? And it's going to neutralize. And when acid and base react together, we get what two guys going to the deli? Water and salt. So you get water and salt, right? And so what happens is you keep on dropping base, keep on dropping base. Well, when the acid is gone, when your Oreo cookies are gone, and you go into wherever your cookie jar or your pantry, and there are no longer any Oreos, then maybe now you need to eat the shortbread cookies or the chocolate chip cookies, something. But Oreos are your fave, okay? So the idea is that then the indicator, then you drop the base down, and now the indicator can bond with the base, and that's where you get the color change. So that's the whole idea of how an indicator works. Once your moles, you can say then that at that point my my moles are equal, but you have to be careful because if you surpass that and you've already had this color change, and that's why it's really important that when you do a titration, you want to really be within drops of having that color change, because otherwise you've dropped too much what? Base into there, right? And now you have an excess of the amount of base, and your pH would actually be more basic than it would be neutral, okay, if you had a strong acid and a strong base. So that's the whole idea of the way that the indicator works. So the first thing is finding the pH of a titration of a strong acid with a strong base. Okay, so it says, what's the pH of a titration of 50 mils of a 0.2 molar HCl with 50 mils of a 0.2 molar NaOH? Well, you could set up a MAVA equals Mervet. You're given volume right here of the acid. You're also given the molarity of the acid. You are given the volume of the base, and you're given the molarity of the base. So what are you solving for? Nothing. Okay, but what the question is asking you is, what is the pH? So here's the idea. If you know that your molarity of your acid and your volume of your acid are equal to the base, then guess what? Guess what's equal to each other? What do we say that MAVA and Mervet are each equal to? Your moles are equal. And if your moles are equal, then that's it. You're good. You're at your neutralization point. And if you have a strong acid and a strong base, guess what your pH is? 7. And it's over. Okay? It's done. So basically, in this case here, you would say that your moles are equal. So it's basically 0.200 molar times 50 mils. And remember, you typically want to switch this into liters because then it'll give you moles, and that's equal to the 0.200 molar times the 50 mils. And so what we're going to do is we're going to say, because they're both strong acid and strong base, and our moles are equal, then therefore the pH is equal to 7. And we're going to say 7.00 to give us 2 sig figs. I think this is actually 3 sig figs. So 7.000 would be your answer. Okay, so let's try the next one. This one says calculate the pH at a random point. So we have not reached the neutralization point is what they're telling us. And we have 50 mils of 0.1 HCl. Let's label it already. So this is representing VA, volume of my acid. And this is the molarity of my acid. And it's 49 mils of the base. So this is my volume of my base. And this is the molarity of my base. Okay, so now I've got MAVA equals question mark Mervet. Well, they're not exactly equal, right? Because if I have 50 mils of a 0.1 HCl, how many mils of my base of a 0.1 molar NaOH would it take to neutralize it? 50. Good, it's got to be equal, right? The moles have to be equal. So in this case, since our molarity is equal, then our volumes would be equal. But in this case here, they're not. It's 49. So it's right before. And the question is, what is the pH right before you've dropped down the 50 mils? Okay? Think about it in your head. Try to take a guess. See what your guess would be. So you know it's an acid, and you've got the acid, and you're dropping base down. And you have not dropped enough base. Take a guess. Okay? Where do you think the pH is going to be? All right. So let's check it. This is basically a 4-step problem, okay? It's about a 4-step problem. Step number 1 is going to be, we're going to try to figure out what our moles are of each one of these, okay? So first thing we want to know is how many moles of each one do we have? So let's write in our Ma is 0.100 molar for our acid. And our volume, I'm going to switch this so that it's in liters. So 0.0500 liters. Question mark. Well, I know it's not equal. I can even do not equal to. Is not equal to a 0.1 molar of my base. And it's 0.0490 liters of my base. So this here is representing my acid, and this side here is representing my base. So now let's calculate that. Okay, so we've got 0.00500 moles on this side, and that's not equal to 0.00490 moles of my base. So that's my moles of my acid, and that's the moles of my base. That's step 1, is figure out your moles. Step 2 is you want to figure out which one is in excess. And the idea is that as much base as can react with acid will. Okay? So the base that you drop down into here, as much of it that can react is going to react. And so how much of your base are you going to have left? None of it. Awesome. All of this is going to be gone. So the question is, how much of this is left? Okay, so what we're going to do is we're going to figure out what's in excess. So we're going to do 0.00500 moles of our acid minus, and I'll just do it down here, minus the 0.00490 moles of our base. And so when we do that, we get 0.00010 moles. Well, the base is all gone, so all we're left with is acid. And which ion matters to us in the acid? H plus. Awesome. So this is our H plus ion, and that's the moles of the acid. So now we have our third step, okay? And the third step is figure out what your molarity is, question mark. Well, we know that molarity is what units? Moles over liters. So we want to figure out the moles over liters. And the only problem is that now our liters are different because we've added acid and base together. So when you go to figure out molarity, you need the new liters. You need to know what your new volume is. So it's moles over liters, but it's got to be your new liters that you're using there. So we know our moles. So our moles are 0.00010 moles of the H plus. And we're going to divide it by the new volume. Well, we had 50 mils and 49 mils, which means we're at 99 mils. But we don't want milliliters, right? So if you take your 99, you're going to go 1, 2, 3 to the left. So what do you get? 0.099 and 0.0, one more zero, liters for our sig figs. But it's going to be 2 sig figs anyway because of that top number. Okay, so now let's calculate this. And what we get is 0.0010 molar H plus. Okay, so now we've got our molarity of our H plus. Keep in mind that when you calculate your H plus, when you do negative log, it cannot be moles. It must be molarity. Okay, it has to be concentration. It can't just be moles. It has to be moles over liters. So the last step, step 4, is find our pH. And how do you find your pH? The equation is negative log. So pH is negative log of our H plus. And so all we're going to do is plug this number right into there, which this is an easy one, because it's 1 times 10 to the negative 3, which means your pH is 3. And so sig figs, so this is equal to 3 we have got 2 sig figs, so 0, 0, and we're done. Okay, so that's basically it for figuring out the pH at a